Optimization is an extension of EVT in the sense that optimization means exactly what you think, to optimize. So optimization is going to be able to take real world situations and find solutions that make sense. So it's actually really similar to what I'm doing with Algebra 2s right now, which is linear programming. So they're looking at a bunch of different functions. They're looking at their points of intersection, and then they're trying to find the one that maximizes or minimizes something. And that's exactly what we're going to do with optimization. The difference is that instead of having to plug in 100 different points that could potentially be the max or mins, we're going to find the critical points, which are the only potential max or mins. So we're taking what could be like 6 options and narrowing it down to 1 or 2. Yeah, there's a lot of calculated stuff here. So if you think about the words greatest profit, least cost, least time, greatest voltage, optimal size, greatest strength, greatest distance. You're really looking for the least or the greatest, aka the max or the min. So optimization problems are among the earliest applications of calc. They emphasize modeling maximums and minimums. If you go into like the econ or the business world, this is where the business applications of calculus come into play. Now there's actually a class that you could take called Business Calc, where it primarily focuses on optimization. So what does the word optimize mean? It means to maximize or minimize an aspect of it. So most profitable production, least expensive shape. So again, all the word optimize means is to maximize or minimize an aspect, meaning to find the least or greatest value. So what I did was give you like an outline of the steps we should take. So you didn't have to write them all out. But ideally what you'll do is read through the problem, identify your given constraints. Sometimes you may need to draw a diagram, and then you're going to find your derivatives. So example number 1, using the 6 by 8 inch sheet of paper, we will create a box that is algebraically maximized by cutting equal size squares from each corner and folding up the 4 edges. When will the dimensions of the box be the largest in value? So what we want to do is draw a rectangular sheet of paper that is 6 by 8. And then what you're doing is cutting out corners from each of those. All of the corners need to be the same, because if you think about a box, the height of the box always needs to be the same. So if you have an open top box, it's not going to have wonky sized heights, or like this side's higher than that side, because that's illogical. So all of the heights need to be the same, or I'd say all of the heights are equivalent to x. And then what that does is that shrinks each of these lengths. So now, instead of the length of the box being 8 inches or 6 inches, the length of the box becomes 8 inches minus both x's and 6 inches minus the 2 x's that you used to fold up the heights. So it says, when will the dimensions of the volume of the box be the largest? So now you gotta go back to your geometry days and say, okay, volume is length times width times height. Well, the length of the box is 8 minus 2x. The height of the box is x, and the width of the box is 6 minus 2x. So we want the largest possible volume. So in order to maximize the volume, I need to find the derivative of the volume. So in order to find the derivative, I'm going to clean up the volume in general. So the volume with no x value, if we don't know what we made the height, is 48x minus 28x squared plus 4x cubed. Again, to maximize or minimize anything in calc, we find the derivative. Set the derivative equal to 0. They're all even, so you can take out a 2. And also all divide by 4. So you can take out 4 to at least get your numbers smaller. So, non-factorable, you have to use your quadratic formula. Quadratic formula gives you blank. Now, if we are told from the beginning that this was a calculator question, I feel like it could be really easy. You would just take your derivative and set it right down equal to 0. And like go to your graphing calculator and then look at the zeros of that function. So do I know how to do that? You could also do quadratic formula like I did on the whiteboard. Like quadratic formula cheat sheet. Yeah, well, the square root of 52 is just a little bigger than 7, so like 14 plus 7 is like 21. It's like just shy of 4. It's just shy of 4. Right? So we would find our two values. My calculator's back here, so doing it in my head. So you have 14 plus second square root 52 divided by 6. You get 3.535. And then you could do it again with 14 minus the square root of 52 divided by 6. And you get x equals 1.13. So then what you would do is check each of these points with the other two dimensions. So if x is equal to 3.535, then you have to do 6 minus 2 times 3.535. And then what happens is you get a negative 1.07. So can one of your sides have a negative blank? No. So what happens is, even though you got that as a critical point, that critical point is invalid because it gives you an invalid dimension. So now we get that the height is 1.13 inches. The width is 6 minus 2 times 1.131, or 3.738 inches. And the length is 8 minus that, which is 5.738 inches. So when it said what are the dimensions of a box with the largest volume, those are your dimensions. So that is your answer. All three of those quantities. So here are technically all different types of volumes that can give you a shape and a quantity that meets those requirements. But what you'll notice is all of the volumes are really different. So like a box that is kind of almost a square has 108. But a box that is long as skinny has 74.25. So what companies do is they try to find a shape that is the most cost effective. And what happens is sometimes the materials of different parts cost different amounts. So like the cylinder part of a Yeti cup is metal, where the top part of the Yeti cup is plastic. So if you ever look, the bottom of the cup is narrower than the top because they use more plastic on top than like metal on the bottom. But then there's also coming into like the fine line of like it has to still stand, it has to not fall over. So canned companies, if you ever like notice the bottoms are a lot smaller than like the width, because again they're trying to save on space and cost. And that's where it all comes from. They have like computer programs that somebody wrote that help them calculate and figure it out. So example number 2, I feel like you've had this problem so many times in your life, but you've never had it in calc. So it says a farmer has 2,400 feet of fencing. He wants to fence off a rectangular field that borders a river. He does not need fencing along the river because the animals aren't going to escape through the river. So what are the dimensions of the field that has the largest possible area? So what you're going to do is imagine that the river makes up one side of the fencing, and logically the river is going to make up one of the longer sides because that's going to utilize the least amount of materials. So we will say that the lengths are opposite each other and the width is opposite the river, just so that we can keep like our variables together. So like your river width and my river width are both. So what does that 2,400 represent in terms of formulas or mathematical knowledge that we have? Perimeter. And in this case, the perimeter is 2L plus W. So you'll replace the P with 2,400. What are we trying to maximize? Area. So we have perimeter as part of our formulas with our numbers, but we're trying to maximize area. Right now, I have area, which I'm trying to maximize, but area currently has multiple variables. So do we know how to maximize something with multiple variables? So we have to use information we know to get rid of a variable. So what we know has to do with the perimeter. The perimeter has 2,400 equals 2L plus W. So what we're going to do is replace one of the variables by substituting with perimeter. So, for example, I could solve perimeter for W. I could say W equals 2,400 minus 2L. And then in area, I could say instead of using W, I'm going to substitute it with 2,400 minus 2L. Mathematically, I haven't broken any laws. I'm just replacing a variable with another variable. So area is now length times 2,400 minus 2L. Or 2,400L minus 2L squared. Now, can I take the derivative of that area and maximize that because it's going to only have one variable and I can set that one variable equal to 0? Yes. So A prime is 2,400 minus 4L. Set that equal to 0. And I get that the length of the field should be 600. I can then use that information to go back to my perimeter formula and solve for W. And I get that the width of the field should be 1200. So it said, what are the dimensions of the field that has the largest area? So my dimensions would be 1200 feet long by 600 feet. Not terrible? Find two numbers whose sum is 20 and whose product is as large as possible. So, perfect. You already got the first part, right? X plus y has to equal 20. And then x times y has to equal some big number. So once again, I can't take the derivative of what I'm trying to maximize with two variables. So what am I going to do? I'm going to use the x plus y equals 20 to get rid of a variable. So maybe I say x equals 20 minus y. So then here, instead of x, I have 20 minus y. So 20y minus y squared equals that product. I'm trying to maximize the product. So I'm going to take its derivative. So the derivative of the product is equal to 20 minus 2y. So then to maximize the product, I said its derivative equal to 0. Solve for y. And I get that the y value is 10. Well, if the y value is 10, then the x value is also 10. And what you should notice is that oftentimes if you're trying to maximize or minimize something, a square shape is always going to be the best. So that's why a lot of things in like naturally occurring instances occur as squares or cubes, because they're so equally lengthed out that they make everything so perfect. Now, what happens with like the farmer, it wasn't a square because we didn't have to have dimensions on all four sides. If the farmer and the fencing had to have dimensions on all four sides, every side would have been 600. Okay? A rectangle is inscribed under the arch of a curve. So here's my curve. Here's the rectangle. Okay? Rectangle inscribed under the arch of the curve. What is the largest possible area that rectangle can have? What dimensions give that area? So the curve itself is y equals the sine of x. So what do we know about y equals the sine of x? Well, we know it starts at 0, 0, and it ends at pi 0. So that means that the max height of the sine curve occurs at pi half comma 1. So we know some particular points on this sine curve. So if the entire length of the sine curve is pi, what would that tell you about the length of the rectangle? terms of this. So if the entire length of the sine curve is pi, what would that tell me about the length of the rectangle inside that curve? What's the longest possible length it could be? Can it be 2 pi? Can it be pi? Could be the length, probably, right? So the length of this piece right here is going to be pi minus something. So what's the somethings that we're subtracting? Well, there's 2 of them, right? So we don't know what they are. We'll just label them as x's. So the length of the rectangle is going to be pi minus 2 x's. We just don't know what the x's are. Here's where it comes to be trickier. This right here represents the height of the rectangle, right? So that height of the rectangle is going to be x units over from 0, because this distance here is 0 to x. So that means that the height of that occurs at x, comma, well, what curve is it hitting? It's the red curve. So if you have a point on side x that also exists on your rectangle, if the x value is x, then you plug x into sine x, so the y value is sine x. Does that make sense? And technically, like this point here would be like pi minus x sine of pi minus x. But we are never going to use that awful point for the height, because then it's just going to get messier. If I make the height on the left side, then at least these are kind of decent points. So area of the rectangle is length times width. Well, its length is pi minus 2x. Its width, or its height, is sine x. So, to maximize it, we're going to find the derivative of it. Derivative of pi sine x is pi cosine x. The second part is a product rule, because you have 2x, which is the first function, times derivative of sine x, which is the second function, plus the sine of x, times derivative of 2x, which is 2. So you have pi cosine x minus 2x cosine x minus 2 sine x. There's no way we would know what these are. So what you would do is go to your graphing calculator, set that derivative equal to 0, and find the x values at which that occurs. Now remember, you would maybe want to restrict your window to be 0 to like pi plus 0.1, because you can't really get an answer outside of 3.14. So if when you go to find your 0, so that second trace go to 0, you want to make sure that you don't find a 0 greater than pi or less than 0. And in the case of this problem, there are 2. Well, what do you know about a derivative and creating a max or a min? So right now we have 2 zeros on that graphic calculator. And they go from positive to negative to positive. So if the graph is positive and then goes to negative, is that first point going to be a max or a min? And if it goes from negative to positive, then this is going to be a. So do I even need to find what the value of b is? Yeah, because what's that going to do? It's going to give me the smallest possible thing. It's going to minimize it. So again, taking into account what the zeros of a graph represent. Like, don't waste your time finding information that is invalid. So you should get 0.710. So that's the height of the rectangle. And then if you wanted to find the length of it, then you would say L equals pi minus 2 times 0.710. And you get 1.72. And then the largest possible area would just be multiplying those two things together. Make sense? So ironically, we're actually going to have homework in the book, because the book actually has some fairly decent homework problems. We'll pick up the rest of this tomorrow and we'll finish the notes. Maybe we'll take our test on Friday and I'll just add 1 or 2 optimization problems now, instead of having that quiz on Wednesday. So this is lesson 4.4. The homework is on page 229, or 239. And we can go to 10.